Hello and good morning. So, in this last lesson, we're going to be talking about the applications of circles. So, how can we use everything that we've learned about circles and their angles, their chords, their measurements to determine applications in the real world? Okay, so before we get started with that, I want to go back and think about some parts of the circle that we need to understand for this lesson in particular. So first of all, we're looking at this figure to the left, and I got you to do this earlier, but with some different parts. But I want you to label each of the parts of this circle using the terms that we've used from previous lessons thus far. Okay, so the first we're going to talk about is this red line, okay, that this arrow is pointing to. So we're referring to that entire line. And what is that called? You may be saying it's called the tangent line. Okay, so that's that part in red. Now blue, the arrow is pointing to this point specifically. So what is that point called on the tangent line? And that's called the point of tangency. Okay, and lastly, we have this arrow pointing to this angle here. Okay, and that angle is outside of the circle. Remember that if it is inside, it's called an inscribed angle, or it may be the central angle if it's referring to the center of the circle. But that angle that is outside is called the circumscribed angle. That is a circumscribed angle. And we're going to talk about the relationship of the circumscribed angle to other angles inside the circle. So let's do that. So right here in this picture to the right, I'm giving you a central angle. Remember, it's a central angle if it involves the center of the circle and then 2 points on the circumference, okay, form that angle. So that's called a central angle. What do we remember about the relationship between a central angle and the circumscribed angle? So that's exactly what this first question is asking. It's saying that our central angle, BAC, is 112 degrees. So we're trying to figure out the measure of BAC and how it is related to the measure of BDC so that we can figure out what BDC is here. Well, some of you may remember that the relationship between the central angle and the circumscribed angle is that they are supplementary. What does it mean to be supplementary? That's something we need to go back and remember in all aspects of geometry. But supplementary means that they add up. Their sum is going to be 180 degrees. Well, if we have 112 degrees, sorry, I dropped my pen. If we have 112 degrees as the central angle, then what does that mean that BDC is going to have to be? So that's going to be 68 degrees, because both of those are going to add up to be 180 degrees. So moving along, so in the last lesson, we talked about inscribed polygons and how inscribed polygons are inside of the circle. So now we're actually going to talk about polygons that are going to be outside of the circle. And those are going to be called circumscribed polygons. And it's going to be a polygon whose vertices, remember that these are our vertices. Okay, and these vertices are going to be tangent to the circle. And those points of tangency are going to lie on the circumference. so this is going to be a point of tangency. Okay? So in this circle, we are given that CAD is 130 degrees, meaning it's a central angle. I'm going to erase all of that. So CAD here is 130 degrees. So we're trying to find the measure of CFD. Remember, those have to be supplementary. So what is CFD going to be? Well, 180 minus 130 should give us 50 degrees. Okay, so now I'm going to give you something a little bit different. I'm going to tell you that this arc CB, is 115 degrees. Remember, what is the relationship between an arc and its central angle? So if the arc is 115 degrees, the central angle should be the same. They should actually be equivalent. So this central angle should also be 115 degrees. But then the relationship between the central angle and the angle we're looking for. So we're looking for CEB. So this is CEB. So we're looking for this angle here. Well, if the central angle is 115 degrees, we know that it and the circumscribed angle are going to be supplementary. So then what is the measure of CEB going to be? It should be 65 degrees. So now let's think back to what we know about circles, okay, and our knowledge of circles and our knowledge of triangles, okay? So using that information, I know that all three, let me label it a little bit. So all three of these arcs, this arc, the blue arc, the green arc, and let's use purple here, this purple arc, they all have to add up to be 360 degrees. Well, we have that the blue arc is 130. We know the green arc is 115. So that should give us 130 plus 115 should be 245. And if we take that from 360, it will tell us what the arc is. It will not tell us what the circumscribed angle is, but it will tell us what the arc is. So 360 minus 245 should be 115 degrees. So that's what this arc is. And again, in relationship to the central angle, that's also what the central angle is. So what does that mean? That angle BGD, what does that mean that angle there, that circumscribed angle is going to be? Well, what is supplementary to 115 degrees? Okay, so that's going to be 65 also. Okay, so using all of that information, now I want us to put it into a little bit of a real-world perspective. So in the first circle, I'm giving you that BD is the diameter. And I gave you that CDB is 44 degrees and DBE is 51 degrees. I want you to find the measures of the angles for the circumscribed polygon. Okay, and here in a moment, I'm going to give you those angles. And then I will give you the answer to number 2 so that you can check yourself. So angle CGB is going to be 92 degrees. Angle BHE is going to be 102 degrees. Angle EID is going to be 78 degrees. And then here, angle DFC is going to be 88 degrees. So those are all of your angles of the circumscribed polygon. So the second question is asking more of a real-world scenario. A satellite requires a line of sight of communication. What's the amount of time needed for a signal to go from one station up to satellite and then down to another station using the information that you have? Okay, so after you have figured this out, it should end up being 0.28 seconds.